It is a full house, so 3 of a kind in a pair is a full house. Well, what if I just put them in a different order in the way I'm physically holding them? What if I wanted to alternate them? So I physically put the king, then a 10, then a king, then a 10, then a king. Is that a different hand of cards? Is it suddenly not a full house? Okay, that's a combination because the order doesn't physically matter in your hand. Do you see the difference between the two? So we're going to highlight the word order in permutation. That's the key. Oh, that went all smudgy. That bothers me. And the hardest thing with these questions is going to be when you read the question on the exam is you have to figure out, is it a permutation or is it a combination? Because they're done differently. 2 different formulas, 2 different ways to do them. So you're always thinking in your head, does the order matter? So physically think about rearranging the objects and think, will that change? So like I said, we're going to spend a lot of time on permutations because they're harder. Combinations, not so much. And we're going to flip to our paper. I just realized I had the mic on mute that whole first time. So hi again, Noah. Hi again, April. They didn't hear my shout out. So example 1, just read to read. Then yes. I be not the English teacher, that's why. So I've been saying read to read and read to understand all semester, and it is really important on the exam because what read to read does is it's slowing your brain down. It's actually de-stressing you a little bit because you're just reading the first time, you're not trying to understand everything. Then the read to understand, by reading it a second time, your brain's actually slowing down and catching every single word. If you just read once and do it, your brain may have skipped words and you didn't even realize it. And there's so many little keywords on the exam. So read to read is you're just reading it, you're not thinking because it's de-stressing you. Now read to understand is we're actually picking out the keywords. If you're not a highlighter or an underliner or whatever, that's fine. Just make sure your brain is picking up all the words. So what is important in the first sentence? Really, it's just the number 5. Gates, yeah, in the sense, but we don't care if this is a stadium, if it's an arena, if it's a building. All we care is there's 5 of something. In the second sentence, what are the keywords? So that you're going to see in almost every single permutation and combination question, because that's what we're trying to find out is how many different ways you can do something. Okay, what else is important? Different gates is going to be important. So to solve these types of questions, we use grabbing my red pen. This sounds so important. The fundamental counting principle. The fundamental counting principle sounds so important. We call it the FCP because we're lazy mathematicians and don't like words. Fundamental counting principle says if one task can be performed in A ways, not A like the preposition A, I can't think of a noun now, stapler, A meaning a variable A, and a second task can be performed in B ways, then the 2 tasks can be formed in A times B ways. That's the fundamental counting principle, says that we multiply. So there's 2 different things we need to do, or 2 different choices, and we're going to talk a lot about choices in this unit. What's the first choice we need to make as we go to our bomber game? Which gate are we going to go in? And we use blanks with the FCP just to represent numbers we're about to fill in. And so this is the number of ways we can enter. What's the second choice we need to make? We need to pick a gate to leave. How many choices do we have as we approach the stadium and we can pick a gate? 5. How many ways can we leave?
4.
Why is it only 4? Why not 5 if there's 5 gates?
Because it said that you're going out a different gate than you entered from.
Yeah, so there were 5. We chose one to go in. Now the question implies we can't pick that one to go out, so there are 4 ways to leave. Fundamental counting principle says that we multiply. That's showing your work. Okay, so you've got a little word or a description of what the numbers represent. You've got the numbers, you've got the multiplication sign. These are not page-long questions like identities or log questions. They're usually one line, maybe one multiplication. How many ways can you enter and leave? By 2 different gates. 20. Now, we didn't actually need math to do that. We could have used logic. We could have numbered the gates 1 through 5 and then started looking at all the different pairings. So if you enter with 1, you can leave by 2. If you enter by 1, you can leave by 3. If you enter by 1, you can leave by. If you enter by 1, you can leave by. So that was how many different gates? If you enter in 1, how many choices to leave? 4. Well, what if you enter by the second gate? So then you could leave by the first, leave by the third, leave by the fourth, leave by the fifth. How many choices? 4. What if you enter the third gate? So how long is that going to take us to come up with all the different possibilities? That's why the fundamental counting principle was invented. It's exactly doing that, just doing it in a shortened version, rather than having to list them all out. Questions so far? Number 2, read to read. Keywords. Mathematicians are often concerned with how many kinds of numbers there are, and so what's an example in the real world why somebody would care? Why do we care how many numbers there are in the world? So to know if there's a limit. So last year, I think it was last year, maybe the year before, what happened in Manitoba when you dial a phone number? You suddenly have to enter the area code. Never had to do that before. Why not? Because we were running out of numbers. So if nobody ever figured out when we were going to run out of numbers, nobody would be doing some pre-planning. What about PIN numbers when you enter your debit card or you take money out of the bank? Typically, how many digits are PIN numbers? 4, sometimes 5. Well, what happens when they run out? Right? Again, somebody's got to plan for that kind of stuff because eventually we're going to run out. So number 2, 3-digit numbers, 3 blanks according to the fundamental counting principle. The blanks are going to represent the first digit. The second blank is going to represent the second digit. And the third blank is going to represent the third digit. How many different digits are there in the world? And what's the difference between a digit and a number? A digit is only one number. So if you didn't know that, just jot that down. A digit is one number. A number can have infinite number of digits. So a digit is one number. How many digits are there? Well, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. There are 10 digits in the world. Okay, so if you didn't know that, jot that down next to your digit definition. Now, 0 is a tricky one because you just need to be aware if we start with a 0. So for example, 019, is that considered a 3-digit number? 019. No, it's considered a 2-digit number. So 013 is a 2-digit number. So for our first digit, we can't start with a 0, but we can start with anything else we want in the world. Kelsey?
What if it's like 0.01?
That would be different with decimal because we wouldn't count those as digits. We'd count them as decimal places. So we're talking non-decimal numbers. Okay? So we cannot start with 0. What are our other choices? 1 through 9, so there are 9 choices for the first number. Now, that doesn't represent us picking the number 9. It represents the number of choices. There are 9 different possibilities we can have for the first digit. Second digit, can we have the 0 now? So could we have the number 102, 504? Yes. Is there any other number we can have or can't have, or any restrictions, we call it, on this middle number? Or can we have anything 0 through 9? Okay, so that's 10 possibilities. What about the last? That one can be anything as well, 10 possibilities. Fundamental counting principle says we multiply. How many 3-digit numbers are there? Offer of 900. Now, what if we didn't know the fundamental counting principle and I said, list out all 900 three-digit numbers? It's going to take us forever, right? That's why the fundamental counting principle exists, a quick way to know how many arrangements of something there are. Now, again, this doesn't represent a number we chose, because this is actually a 5-digit number if we had 9, 10, 10. This just represents choices. So you might want to jot down a blank just represents choices. It's not an actual selection of the number. Blanks represent choices. Well, those are the easy questions. Now we're going to go into permutations with restrictions. Need to talk to the ladies for a second. Ladies, the most stressful thing you are ever going to go through, besides childbirth, not that I've been through it, but I've seen pictures, the most stressful thing you're ever going to go through is planning a wedding. Worst possible date ever, because everybody hates everyone, and this family doesn't get along with this family, and grandma hates Uncle Fred. It's just terrible. The worst part of it is trying to figure out the seating plan. Because who doesn't want to sit next to who, and who has to sit with who, and then you got Auntie Mary that's got 14 kids, and they all want to sit together. So that's when you get into restrictions, is when people have to be together, or objects have to be together, or they can't be together, or there has to be a space in between them, or they have to be 15 tables apart from each other. It's not fun. So restriction is a condition that limits the total number of possibilities. Some examples, what you'll see in the questions is must start with, must end with, must sit together, must not be together. And I've grouped the examples into types. So example number 3 is going to be about seating. So people who need to be together don't want to be together. There's too many chairs, there's not enough chairs, et cetera, et cetera. Number 4 is going to be about creating pin numbers, so putting numbers in order. And the last one's going to be like the ultimate restriction is when it has to be even and divisible by 5 and this many digits and can't be with this and can't start with this. So I'm just grouping them into different categories. So example number 3, just read the first sentence. Now let's read to understand in the main sentence what's important. Any other keywords? Yeah, I agree. There's nothing else. Some people think arrangements, but you'll see that in combinations as well, so it's not an indication, it's a permutation. So we're going to have these 5 people, and we're going to seat them in 5 seats. That's the easiest one, 5 people, 5 seats. Then we're going to take away 2 of the seats. And what's going to happen to the number of seating arrangements when there's only 3 seats? What if there's an extra seat? What if Jack must be on the first seat, because Jack's a pain in the butt, you'll find out an example. Oh no, now he has to be in the middle. Now he wants to be at the end. Then there's Jack and Jill, have to be together, then they break up, refuse to sit together. Those are all the different possibilities we're going to look at with seating. The only thing that's going to change is the number of people. So maybe the example or the homework question will give you 6 people or 5 people. Or maybe it's not people, maybe it's books. Okay? Maybe it's digits. Whatever, it's going to be the same as this, whether it's people, objects, numbers, whatever. Okay, example A. 5 people, 5 seats, how many blanks? How many choices do we need to make? This is not a trick question. 5 people, 5 seats, how many blanks? 5. So imagine one of these rows, let's pick Rob's row because it's the emptiest, completely empty. Rob walks in the door, he can sit anywhere he wants, any of the desks. How many choices does he have? He can sit anywhere, he's got 5 choices. He picks the seat at the back. Kelsey comes in, decides he wants to join Rob, because Rob's so lonely and sneezy back in that desk there, so he wants to join him. Well, how many choices does he have if Rob's already sitting in the last desk? Unless he's going to sit in his lap, and that's just really weird. So Kelsey sits down, he picks a seat. Janae walks in. She wants to sit in the same row because it's now like the coolest row in the entire room. How many choices does she have? She picks a seat. Stephanie walks in. How many choices are left for her? And David's late, so he's only got how many choices left for the very last seat? 1. Have we used a calculator yet? No. So typically with these, they're non-calc when the numbers are small. I'll show you some later when they are calc. Now, when you're multiplying this in your head, is go with whatever your brain sees first. Some people will see the 5 times 4. Some will see the 5 times 2. Go with what your brain sees first. So if your brain sees 5 times 4, do that first. What's 5 times 4? Now, if your brain sees the 3 times 2, do that next. What's 3 times 2? Well, what's 2 times 6, which will give you 20 times 6? 120 times 1, 120 different arrangements. Okay, don't think you always have to multiply numbers in order, but if your brain sees it as 5 times 4 and then times 3, that's fine, but just go with whatever your brain sees first. So that is 5 students, 1 row of 5 desks. There are 120 different ways I could arrange them. 1 row, 5 desks, 5 students. How many rows in this room? 6. How many desks in each row? 5. How many desks does that make? 30 desks are in this room right now. How many people are in this room right now? 13. Okay, at the end of this class, I'm going to ask you how many different seating plans I could make with 30 desks and 13 people. Okay, so just keep that in the back of your mind. Okay, let's see what's going to happen now if we take away some seats. So now there's only 3 seats, but there's still 5 people. What's the implication at the end? What's the implication, meaning what does it imply? If there's only 3 desks, not everyone's going to get to sit. So in the end, there's going to be 2 people standing. We're not cramming 2 people into a desk. We're assuming whoever the first 3 are, they're the people who get to sit, or whoever I choose first. So 2 people are going to be standing. How many blanks? Not a trick question. 5 people, 3 seats. How many blanks? 3 or 5? Why not 5? Well, let's try with 5 first, and then you should see why not 5. So what's going to happen is 3 desks, 2 desks, 1 desk, 0, 0. And what happens when we multiply by 0? So that's an indication that it's not 5 blanks. It's going to be 3 blanks. Always go for the lower number of blanks. So 5 people, 3 desks, 3 blanks, because 3 is smaller than 5. So blanks always go with the lower number. So now we need to switch our thinking a little bit. These blanks represent what? The desks. They don't represent the people anymore. These are the desks. So this is desk 1, and desk 2, and desk 3. Now, we're not going to say desks are choosing people because that's just weird. So we say how many people could choose the first desk if there's 5 people standing in the room. 5 people could choose the first desk. Somebody does and somebody sits down. First come, first serve. There's now 2 desks. How many people could choose the second desk? 4. Somebody picks it, somebody sits down. 3 people standing. How many people could choose the third desk? 3. What's the implied for the 2 other people? They don't get to sit. 5 times 4 times 3. Now just look at that mathematically. It's interesting. 5 desks was 120. 3 desks was 60, which is half, but the desks aren't half. Interesting. We'll come back to that. Third situation is when there's more seats than people. Okay, so we have 6 seats, 5 people. How many blanks? Go for the smaller number of blanks, otherwise you're going to end up putting zeros, which isn't going to work. So 5 blanks or 6 blanks? 5 blanks. What do the blanks represent in this situation? So what is that smaller number, desks or people? So person 1 all the way down to person 5. First person walks in, how many choices do they have? 6. They pick a desk and sit down. Second person. They have 5 choices. They pick a desk and sit down. Third person. Followed by? Followed by? What's this implied? What happens to that extra desk? No one sits there, and that's fine. We have empty desks in this room. Okay, multiply, go with whatever your brain sees first. A lot of people will see the 5 times 4 first. That's fine. Multiply through, don't shout it out, give everyone a chance. This is just how my brain saw it. I saw the 5 times 4 first because I like 5s, which is 20. Then I was going to multiply by the 6, and I'm like, 3 is easier. What's 20 times 3? 60. Then I'm like, okay, I'll times by the 6. What's 6 times 6, which would give us 6 times 60? And then times 2, so 36 times 2. 720, so there we go. That's about as hard as they're going to ask you to do without a calc. Okay, you should be expected to multiply 5 smaller digits together. Anything bigger, typically, that's going to be a calc question. How are we feeling so far in permutations? Good. D, oh, Jack. Okay, 5 seats. Jack must be in the first seat. I'm going to put a J under the first blank. What do you think J represents? Jack. That's showing your work. As long as I have something there, the marker's going to understand you know that there's a condition on the first seat. So how many choices for that very first seat? Or how many choices did Jack have? He has to have the first desk, can't see, needs to be at the very front. So that's a 1 choice. He has to have the first desk. Do we care who sits behind him? How many different choices could sit behind him? How many people? Someone picks a seat and sits down. How many could be in the third desk? Followed by? Followed by? Fundamental counting principle says that we multiply. Offer. That sounds confirmed. Okay, that's called a restriction because Jack is restricting the first seat. It's the same thing if I had 5 books and I said the smallest one has to be first. Same thing if I have 5 numbers and the first digit has to be a 2, for example. Okie doke. Jack, middle. Doesn't want to be in the front anymore. I'm too scary. Has to move a little seats back. J in the middle seat. Do the restriction first because it's the easiest. So there's 1 choice for the middle seat. Has to be Jack. What about the first seat? Second seat? Fourth seat? Last seat? Exactly the same numbers as last time gives us 24 different possibilities. Go back and look at A for a second. And A was 5 people, 5 seats. Didn't matter where anyone sat. What was the total number of arrangements with 5 people, 5 desks? Doesn't matter. 120. 1 person wants 1 particular desk. What are we now down to? 24. That's interesting. That's a huge jump from 1 person. Jack must be on the end. Now you need to be careful with questions like this because you're probably visualizing rows like you're seated in. But do rows have to be where people are front or behind you? No, if you think in the gym, what are rows? Horizontal, right? It's where people are beside you. So if the question doesn't specify, we're going to assume it's horizontal. So Jack could be on this end, but he could also be on the other end. This is called cases. So this is case number 1, case number 2. If they want a specific end, they'll say the first seat. That's why this just says at the end. It's very ambiguous. So at the end means either end. And again, sometimes it's hard to visualize when you're thinking vertical rows. So you always need to think seating can be side to side, and at the end could be the left side or the right side. Okay, maybe he's at the bottom of the game and pees a lot and really needs out quickly. That's why he wants to be at the end. Okay, so case number 1 is the exact same we did in D. He has to be in the first seat. Second seat, and then 3, and 2, and 1, and we already know that that's 24. What about the second case? Well, again, do the restriction first because it's the easiest. How many for the last spot this time? What about the first? 4, then 3, then 2, then 1. What do we do with cases? We add them. So we have 24 for the first situation, 24 for the second situation, total number of permutations, 48. So in red, I'm just going to make a note, this was on the end, okay, because it doesn't specify which end. Grabbing my red pen, there's two key words in mathematics, which are and or. And mathematically always implies multiplication. And that's why we do the fundamental counting principle, we multiply. Because, for example, in this one, we need Jack and a second person, and a third person, and a fourth person, and a fifth person. That's why we multiply. Or is the cases. It could be case 1 that he's on the left, or it could be case 2 that he's on the right. Could he be both? Could it be an and? Could he be on the left and on the right? No, so or always implies adding. If you keep those two little words in your head, it'll make some of the more complicated permutations easier. Think, is this or is it and? Or is multiplication, and is always going to be addition. Okay, G. 5 seats, Jack and Jill must be together. I'm going to pretend for a second they're in the first and second spot. Does it matter who's in the first and who's in the second? So this could be Jack or Jill. And then the second one has to be the other. So how many possibilities for the first seat if it could be Jack or Jill? 2. How many possibilities for the second seat if it's the other one of them? 1. So they pick seats, they sit down, first and second seat. Does it matter who sits next to them? So how many people are left? 3, followed by 2, followed by 1. Offer of 12, confirmation. But what if they're not in the first and second seat? What is the second case? They could be in the second and third seats. Does it matter who comes first? How many choices for the first spot? Because we don't care who sits at the beginning. What about the spot after them? 2 people are left, and the last spot, total has to be 12. But what if they're not in the second and third spot? They could be in the... They can't be first and third because they have to be together, right? So this would be third and fourth. So 2 and 1 representing Jack and Jill. The remaining spots have to be 3, 2, 1 to represent all the other people. Total is. But what if they're not in the third and fourth seat? What's the next possibility? Hunter, I didn't grab my phone. 2, 1, 3, 2, 1. Total is? What do we do with all these 12s? Why do we add them? Because it's an or. They can be in the first and second, or the second and third, or the third and fourth, et cetera, et cetera, et cetera. Total number of possibilities. 48. That's the long way to do things that need to be together. Grabbing my red pen, I'll show you the short way. So any kind of objects that need to be together. Okay, could be movies on a shelf, could be people, could be numbers within or digits within a number, anything that needs to be together. So I'll do the example with Jack and Jill. I'm going to circle them as a group and start with 2, 1, just like we did last time. Then instead of doing the 4 cases, what I can do is imagine them as one unit stuck together. I need to keep them together because I can't put anyone in between them. So if I count them as a person, Jack, Jill, there are 4, 3, 2, 1 possibilities. So the first group could be Jack, Jill, or person 1, or person 2, or person 3. What we've done is just combine all these into one. Okay? After that, doesn't matter. That's the short way to do it. Some people like the short way, some like to write out all the possibilities, completely up to you.
Couldn't you just do one with 2, like we did before, and then
Isn't that exactly what I just did? Yeah, and you're like one step ahead of me as I'm going to write it in words in a second. Okay, so within the circle, that's the number of objects that have to be together. The number up here is the remaining objects plus 1. And 1 because we're counting them as a group. So we're putting them in the first seat, then the second, then the third, then the fourth. Does that answer your question? You were like literally a minute ahead of me there. H. Oh, they break up. They don't want to be together. Sorry, Chantal? Yeah. Okay, so now they refuse to sit together, which is more common than you think, especially at weddings. Everyone hates everyone in a family, and then you got his side that hates her side. It's just crazy. So think about this. There's two possibilities. You're either sitting with someone or you're not. There's only two possibilities. You're either sitting with someone or you're not. So you're either sitting beside Mrs. Hill right now or you're not. Are there any other possibilities to that? You either are or you aren't. So to do objects that refuse to be together, what we're going to do is the total number of permutations without restriction, and we're going to minus off the amount if they are together. If we take the total and minus together, what does that have to leave us? When they're not together. Okay, so let's do the example, then we'll write it in words. So what I call the total is no restrictions, nobody has to sit anywhere, nobody cares. So that's 5 seats, 5 people, nobody cares who's in the first spot, nobody cares who's in the second, everybody's happy with wherever they sit. That's what we did in A. That was no restrictions. Anyone sits anywhere, and we said this was 120. Then we're going to subtract when they are together. And we just did that above. And we said it was 48. So from G. And that has to equal when they're not together. So 120 minus 48. So if you can't do the subtraction right away, subtract 20, because then you get down to 100, and then you've got to subtract 28. Sometimes it's easier to subtract 30 and then add 2 back. Offer of 82. Correction of 72. Confirmation of 72. There's when objects cannot be together. If you want to do it the long way, good luck. Because then you have to get all the possibilities if there's one person in between them, if there's 2 people in between them, if there's 3 people in between them. Then if they're in the first and third, first and fourth, first and fifth, what if they're in the second and fourth? So it's just too many possibilities to list out. Try to list out 72 possibilities. Easiest way to do not together is total minus together. Okay, so this is no restrictions. Anyone, anywhere, nobody cares. This is together from part G. And that will always equal the not togethers. How many desks did we say are in the room? 30. How many of you? I thought you guys said 12, but maybe we recounted without me. Did we say 13? 13? Okay, so 30 desks, 13. You don't need to write this down, but let's do it together. How many blanks do we need? 13 blanks. Why not 30 blanks? When I'm drawing multi-blanks, by the way, I tend to group them in threes. I don't know why. Threes are just my favorite number. So I went 3, 6, 9, 12, and 1 is how I got 13. No seating plan. You walk in the first day. I don't care where you sit. First person in the room has how many choices? Picks a seat, sits down. Then? Multiplication or addition, and why? Multiplication, why? Because it's an and, because the fundamental counting principle says we need to seat the first person and the second and the third and the fourth. Grab your calculator, tell me how many different seating plans we can do in this room with 30 desks, 13 people. Ooh. This is not a factorial, though.
No, because then we can say 30 factorial minus 17 factorial.
I wouldn't do that yet. Fingers tired yet?
A lot.
More specific.
Goes up to
7.5 times 10 to the 17 confirmation. I don't even know what number that is. I don't think it has a name. So when you're like, oh, that teacher hates me, they're picking on me. No, we're not. There's this many possibilities. We're not doing it to annoy you. There are a bajillion, trillion different seating plans. Now imagine an average wedding has how many people, Mrs. Hill? 150? Yeah, imagine trying to seat 150 people when these people can't be together and these ones can and these can't. That's why people elope. That's it right there. Let's look at the same kinds of restrictions, just now instead of people, we're going to do digits. So you need to create a 3-digit PIN number for your bank cards, and you can only use the digits 1, 2, 3, 4, 5. I would not bank at this bank because that doesn't seem really secure to me, but... And I said it, and other people say it, but PIN number, wrong. What does PIN stand for? Personal identification number. So we always say PIN number, but then it's personal identification number. But I say it too. 3 digits, only 1, 2, 3, 4, 5. Okay, so make sure you catch the word only in there because it's limiting you to these things. So this is a restriction because there's only 3 digits. It's a restriction because they're restricting you from 1 to 5. How many different pins can you create? 3 digits, 5 choices, how many blanks? 3. Go for the lower number, otherwise you're going to end up putting zeros. How many choices for the first digit of your PIN? And the second? And see, now we get into, is it 5 or is it 4? Well, people, it has to be 1 less because they've sat. But with numbers, could you have repeating digits in a number? Could you have the PIN 555? Could you have 112? Could you have 334? Sure. So how many choices for the second? And for the third? Multiplication or addition? Because? And. We need a first and a second and a third. Total is? Yeah, I'm thinking hackers could crack that pretty easily. That's why we don't use 3-digit pins. Just to note again, that doesn't represent you picking the number 555 as your PIN. It represents 5 choices for the first, 5 for the second, 5 for the third. How many start with a 3? So here's an additional restriction is the very first digit has to be a 3. So just note how I've showed my work there by putting a little 3 underneath. How many choices then for the first digit? 1. Okay? Again, that doesn't represent picking number 1. It represents 1 choice. What about the second digit? Do we care? Nope. So there's 5. And the last one, total is? So if someone looked over your shoulder and saw your first digit was a 3, they only have to try 25 possibilities before they get all your money in your account. How many are even? Well, what determines whether a number is even? What is a 2 or 4 or 5 or whatever? The first one? It's the last one. So last one is always determines what's even or odd. And our only choices for this are the 2 or the 4, because we only have 1, 2, 3, 4, 5. So do the restriction first. How many choices for the last digit? 2. Do we care what the first digit is? Do we care what the second digit is? Total of even numbers? So you're better off security-wise picking an even or an odd. How do we know there's more odd numbers? Well, if the total is 120 and we know 50 of them are even, how many are odd? 75. How many use only odd numbers? Does that mean the number itself is odd? Yes, but what does it mean about the first 2 digits as well? Odd. So this is not just an odd PID number. It's telling you you can only use odd numbers. One, 2, 3, 4, 5. How many of those are odd? Can we pick the same odd number for the second one? Sure. Can we pick the same one for the third? Sure. How many different possibilities? 27. There's a sample of restrictions with numbers, or could be letters, or could be any kind of object that you're picking. Sample 5 is going to be as hard as it gets. These are like uber restriction questions. Read to read the main sentence. Because the question says no. Do you ever start reading a word problem on an exam or the test and you feel your heart going a little bit faster? You're like, oh my God. That's why we read to read and then we read to understand. Because the read to read, when your heart's like, oh my God, there's so many words, what it's doing is just calming you down. Second time, now you're going in to understand. If you try to do both at once, your brain's racing ahead and you're going to miss words. Okay, so now we go, okay, it's okay. Now we go in, what do we need to know from this? Only these digits. Repetition's not allowed. So we did repetition in the last one. This question is specified not allowed. Okay, A, what do we need to know? Apparently nothing. 4-digit numbers greater than 6,500. I'm going to start with 4 blanks because I know it's a 4-digit number. Now I'm just going to use some logic and I'm going to systematically go through the numbers and see what can we start with. Can we start with a 2? Could we start with a 3? Could we start with a 5? Can we start with a 6? Okay, so that's going to be case number 1. I can start with a 6. What about the second digit? Could it be a 2? So can I have 62 something something? No, why not? Has to be greater than 6,500. Can the next digit be the 3? Could it be the 5? Could it be an 8? Could it be a 9? Yes, any of those are going to be bigger than 6,500. What about the third digit? Could be anything. What about the fourth? Could be anything. Okay, 6 means I have 1 possibility for the first digit. How many possibilities for the second? Because I'm just doing the 6, I'll do the 8, 9 in a second. I'm just starting with the 6th. What about this one? So how many digits do we start with? 6 of them. How many have we already used? 2. We filled 2 spots. How many, therefore, are left? 4. Let's make a note. This is because there's no repetition allowed. So we had 6 numbers. And we used 2 for the first and second digits. had 6 numbers, we used 2. Now don't think we used 4. Those were just our possibilities. We physically put 1 in the first spot and 1 into the second spot. If the question had allowed repetition, it would be just like the one before, but this one specifically said no repetition. Okay, what about the last one? So we filled the first spot, the second spot, the third spot. How many numbers are left? 3. Again, multiply what your brain sees first. Some will see the 3 times 3, some will see a 3 times 4. Total is? Again, just note the amount of work that I showed. Okay, so I have a 6, I have some numbers here representing. If you just have 4 numbers with no explanation, you're going to lose a mark for that. These questions on the exam, they will typically say, briefly explain your calculations. You're going to see that if you've already started the route. Briefly explain your calculations. This is briefly explain. It's not a paragraph, it's not a novel, it's not 3 pages of the exam. Briefly explain, just a little note why this number is what it is. Okay, second case. Can I start with an 8? Does it matter what comes next? Okay, so how many possibilities for the first? 1. How many possibilities for the second? 60. Case number 3. Can I start with a 9? Yes. Does it matter what follows? No. So we're going to have the same as above. What do we do with the 3 cases? Add them. Why? It's or. It's case 1 or case 2 or case 3. Case 2 and 3, you can combine if you wanted to. So if you wanted to combine those, you would have 8/9, which would give us 2 possibilities, then 5, then 4, then 3. You cannot combine case 1 with any of the other cases. So if you wanted to smush these 2, you could. You cannot combine. Why does this one have to be its own special case? Why does this one have to be? Because there's a restriction on the second one where these do not. So if you want to list them out separately, great. If you want to combine these 2, great. But this one has to be its own because it's got the double restriction. How are we doing so far? No one's crying yet. That's a good thing. How many 3-digit even numbers are there? Turn and talk. How many blanks? Where's the restriction? Oh, frozen, thank you. Where's the restriction? Which means? Okay, so the last one can be 2, comma, 8. You could also just write the word even. The marker's going to understand what you know by that. Completely your choice. Okay, number. But we have 6 numbers. But we used 1 over here. Okay, so out of our 6, there's 1 gone, and then another 1 gone. Total is? Okay, so if we go back and look at 4C, it says how many only use odd numbers versus how many numbers are odd. So an even number is just this. If we can only use even numbers, this would change. Does that answer your question? Okay, last one was an exam question from 3 years ago, maybe 4 now. Can't believe it's 2015. It's going too fast. Okay, let's work through it together. So you talk, I'll write. This is where you talk, and then I write. They missed the talking part. Don't quite get that. Tell me how many blanks. Agree, disagree? Why?
Anything less than 400 could still.
Okay, any restrictions?
Oh, me?
Mhm.
Because anything less than 400 could still have 3 blanks.
Okay, so can't have 4, then it would be bigger than 400? She's pondering. Okay, any restrictions?
The first number has to be either 2 or 3.
Agree? Okay, any restriction on the second? Okay. Okay, why 2, I heard someone say? Why a 5? You used 1 of your 6, and then you've used 2 out of your 6, okay? I heard 36.
No, I said,
Oh, oh, oh.
like of your 6,
Mhm.
6 away.
You've used 1, 2. So you got 4 numbers left. So you have those 6 numbers like in a bag, right? You pull out 2. Total is 40? You would have gotten 1 mark out of 3 on the exam for this question.
Because you could have 2 digits or
Yeah, and that's the trick with permutations is, could it be a 2-digit number and be less than 400? Yes, so this is case number 1, the 3-digit number, but we need to do case number 2, which will be the 2-digit number. And then case number 3 will be the 1-digit number. So don't get in the trap of thinking 403 digits. It just says how many numbers are less, so it could have any number of digits. Any restriction on either of these? Okay. Offer of 6 and 5. Okay, total is? The 1-digit number? What do we do with the 3 cases? Why are we adding? Has to be either 3 or 2 or 1-digit number. Total is 76. Show me a thumb on permutation so far. I'm liking it. I'm kind of liking it. I'm liking it. Good. I'm okay with that right now. Tomorrow, a whole bunch of you are